Swayam Prabha. Digital India. Educated India.
So, we will just continue from where we left off. We were talking about the definition of metric, which basically talks about the distance between two vectors. Okay. And what I want to do is slightly change the notation, because that is the notation which we are going to use from now on. Okay. Yesterday what we did was we used x, y, z to represent the coordinates. Okay. But supposing you want higher dimensional vectors, there is no alphabet after z. So, we are stuck. So, we overcome that problem by using this different notation. Okay. So, what I am saying is u, the vector, I will say has u1, u2, u3 up to un. So, the different coordinates, the different elements of u are now going to be represented by the subscripts. This way I can take n as large as I want, 5,000, 10,000, 20,000, whatever. Okay. And if I have v, a vector, I will similarly have v1, v2, v3, vn. So, basically ui represents the ith element of the vector u. Okay. So, earlier we had x, y, z, but so using x, y, z, x1, y1, z1, x2, y2, z2, I am just changing it now. So, subscript 1 represents the first coordinate, subscript 2 represents the second coordinate. Okay. That is just the change in the notation. So, this is the notation which helps us generalize to n coordinates. Okay. So, with this notation, if I want to represent metric the way I defined yesterday, so how do I represent metric? How to represent metric with this notation. Okay. So, one possible definition which we saw yesterday, the D2 metric, I think this is D2 metric, I can write it compactly as sigma ui minus vi squared to the power half. Okay. So, take the first coordinate of this, subtract, square, add it to second coordinate minus second coordinate squared, and so on and so forth. So, basically instead of having x, I can sum over I can't sum over x, y, z. Okay. So, this basically tells me the summation is over I equals 1 through n. Okay. So, this is allowing me to represent my, so tomorrow if you have to calculate this metric, you can use this formula to do it. If you have a very large dimensional vector, you can just write a computer code, it will automatically do the calculation. Okay. So, this is one definition of metric. We saw another definition of metric as sigma I equals 1 through n ui minus vi. okay, the mod of that. And there is a third definition, which is this, which is the maximum of ui minus vi over all I. So, these are basically three different definitions of metric, okay, and these satisfy the axioms that I wrote down yesterday, okay. So, I said metrics have to satisfy certain axioms. Distance between u and v must be the same as v and u, the distance must be positive. If it is 0, that means the two vectors are identical. So, things like that, okay. So, basically I am saying these are three possible ways by which you can define the metric. All these are valid definitions of metric or distance, okay. So, I mean, why is this 2 coming here? It becomes squaring into the power half, is all to the power of 1, and this. So, what do I do here? I take the difference between each coordinate, the absolute value, and find the maximum of that. So, that is a metric, okay. So, that is what I mean. I find the difference between the two coordinates and then which is the maximum, okay. That is a gives you an idea about the distance between the two vectors. Now, what I want you to understand is that let us take an example. Let us say u is 1, 3, 8 and v is 2, 4, 5. Two different vectors I have taken, okay. So, I am just restricting myself to 3 coordinates. So, this is basically I do not need to put the comma here, there are 3 different elements, okay. So, this is u1, u2, u3, or what you are comfortable with, x, y, z maybe, v1, v2, v3, okay. So, if I want to calculate d2 of u comma v, what would I do? I have to use that formula there, okay, and that is sigma ui minus vi whole squared to the power half I equals 1, 2, 3, okay, and this will turn out to be ui minus vi is 1 squared is 1 plus again 1 squared is 1 plus 3 squared is 9 to the power half. So, this is square root of 11, okay. What about d1? It would be just take the absolute value of the differences. So, now d1 would be 1 plus 1 plus 3, which is 5, yeah, the problem. And what about d infinity? It will be this is 1, this is 1, this gives me 3, the maximum of this is 3. So, the point I am trying to make here is that you are not going to get the same value for the metric, okay. The distance is this d, this metric is just a measure of how they are different. It's like you can think of it as choosing different scales, okay. Though it's not really scales, not units, but this is just a measure of how far away these vectors are. So, if you want to compare the distance between 2 vectors and another 2 vectors, you have to use the same metric and do this comparison. So, this is just to illustrate that you will get different values for the metric depending on the definition you use, okay. And but if you take vector u and v and u and w, if metric of u and w is much higher than u and v, then you know that it's sufficiently far away, u and w is sufficiently far away compared to u and v. But when you do this comparison, you should use the same metric. Okay? So, that is just to give you an idea that this is what we have to do. Now, if this and a valid definition of a metric. Okay. So, what is d of v comma u? D of v comma u will be just have to substitute here, instead of u put v, instead of v put u. Okay. Now, clearly this is the negative of this. Okay. So, what I am saying is d of v comma u is the negative of d of u comma v, but what we said is the axiom which has to be satisfied is d of v comma u must be equal to d of u comma v. Okay. So, this violates an axiom, and so we cannot use this. Now, where exactly will this business of metric be used? Supposing you are solving some system of nonlinear equations, okay, you will solve it by some iterative method, and when do you know that this iterative method has converged? When two successive iterates are close to each other, right? I mean, that is what we do when we do the numerical solution. So, when I am saying two successive iterates are close to each other, what I am doing is I am calculating the metric. Supposing your problem is not just solving one variable, but a bunch of variables. Okay. So, you will have to at every iterate you will get a vector. So, in two successive iterates you have to find out if are they close to each other. What is the distance between these two iterates? If they are close to each other, then you say your problem is converged. You specify some tolerance, must be less than epsilon or something. So, this is one place where this concept of metric is used. You have been using it when you write your code for solving nonlinear equations. You have been using this, okay. But you can use any of these definitions. You can use the D2 metric, you can use the D1 metric, you can use the D infinity metric. It does not matter, okay. And so, that is the point. So, where exactly a practical application to find convergence of sequences when you do a numerical solution for nonlinear equations. So, this any of the valid definitions can be used to determine convergence of an iterative scheme. For example, I will just write down Newton-Raphson method. Okay. When you do Newton-Raphson method, you do an iterative scheme to solve nonlinear equations. You want to make sure the two things are close to each other. Okay. So, now I want to discuss the next thing, which is the length or norm of a vector. And again, the norm has to satisfy certain axioms. Okay. For example, the norm of u, now we are talking about only one vector now, earlier distance was between two vectors u and v. Okay. Now we are talking about norm is length only for one vector. Norm of u has to be greater than 0 if u is not equal to 0, and norm of u equals 0 if u equals 0. Okay. So, vector is 0, length is 0. If the vector is non-zero, it has a positive length. I am talking about length. Okay. It has to be positive. The second thing is norm of this. So, this is the sign I am going to use for norm, 2 lines. This basically tells you length. Okay. Norm of alpha u, when I multiply this by scalar, is going to be absolute value of alpha multiplied by the norm of u. And third one is norm of u plus v is less than or equal to norm of u plus norm of v. This is a triangle inequality. Okay. Length of one side of a triangle is less than the sum of the other two sides. It should be less than or equal to, because I have not put it, you are right, correct. So, yesterday basically I am going to is less than, but if one of these is 0, then equal to will come. Okay. So, correct. His question is this less than or equal to or less than? Yesterday when I talked about metric, I put less than. Now I am putting less than or equal to. Less than or equal to I am putting, because if v is 0, I am trying to make it more general. If v is 0, the norm of u can't be less than norm of u. Norm of u will be equal to norm of u. So, now what are possible definitions? Again, I can have multiple definitions for norm. Okay. And there can be different definitions for the norm. I am going to call this is what you are used to, the standard definition for length of a vector in physical space, in 2-dimensional, 3-dimensional space, which is the Euclidean length, which is sigma ui squared to the power half. Okay. The terminal point of the vector, what is the distance of this from the origin? That is what we said. So, then that could be the analogous thing, which is sigma ui, and all these summations are over the n coordinates. Okay. And then I have the infinity norm, which is the maximum of so again you need to satisfy that these definitions satisfy the axioms. Okay. So, as long as these definitions satisfy the axiom, you can use this for determining length. But like I showed in the case of the metric, when you use different definitions, you will get different values for the length, but that is just the way you are measuring it. Okay. Now, there is a hierarchy of concepts which arise. For example, if the norm or the length is defined, then automatically a metric is defined, but not the other way around. Okay. So, for example, and like I told you, the axioms for the norm, they involve the concepts of scalar multiplication and vector addition. So, this has to necessarily be defined on a vector space, because when I add two vectors, I need to get a third vector in the same space. When I multiply by a vector, by a scalar, I need to get a vector in the same space, whereas metric I do not have that. Okay. So, that is something you have to be clear about. So, the norm axioms involve concepts of scalar multiplication and I do not know, vector addition. So, the norm has to be defined on a linear space vector space. Okay. Well, the metric does not have to be defined on a linear space. So, such a space is called a normed linear space. Okay, it is a linear space, norm is defined on it. Okay, length, concept of length is defined, and I am going to, whereas a metric space, it does not have to be a linear space. A metric space, what is a metric space? A space in which metric is defined, okay, does not have to be a linear space, since metric does not involve concepts of scalar multiplication and vector addition. So, basically all I am saying is, if a norm is defined, we can use it to define a metric. I mean, you saw those formulas I wrote down for norm 2, norm 1, norm infinity, and the formulas for D2, D1 and D infinity, they were very similar, right. So, for example, I can say D of u comma v can be written as norm of u minus v for any of the definitions. So, we basically want to find the distance or the metric between two vectors u and v. All I have to do is find the length, or if I find the length, I get the metric. Okay. So, that is basically what it is, and you can easily check, because what was this definition? Sigma ui minus vi whole squared to the power half, and this is also the same thing. Okay. And similarly, you can check for the other definitions, the D1 and the D infinity. You can get one. So, basically, if a norm is defined, automatically a metric is defined. A normed linear space is a metric space, but not the opposite. A metric space is not a normed linear space. Okay, that is what you have to be clear about. The next thing I am going to talk about is this concept of inner product. So, this inner product is just a generalization of this dot product that you are comfortable with, okay, and it basically is something which represents the angle between two vectors, okay. What you are doing is you are taking a projection of one vector on the other. In fact, if the inner product between two vectors is 0, what that means is those two vectors are actually perpendicular to each other, okay. When you take the two vectors perpendicular to each other, you take the projection and get 0, but if the angle is not 90 degrees, you will get a projection, okay. So, that is the geometry concept, but we are trying to extend it to a higher dimensional space. Again, inner products have to satisfy certain axioms. Now, these are important because tomorrow when I am going to solve, proceed with actually solving some problems, we will be using these axioms, okay. So, inner product, this is a generalization of the dot product. Measures the angle or projection between two vectors, okay. So, again the axioms which have to be satisfied are, first one is this is this bracket, this is the symbol for inner product, okay. So, is also greater than sign, so do not get confused. So, this is the symbol for inner product. This is greater than 0 for u not equal to 0. And inner product of u with u is 0 implies u is 0, okay. Now, if you take two vectors u and v, u with alpha v, okay, this is equal to alpha times inner product of u with v, which is equal to inner product of alpha u with v, okay. And finally, the third one is inner product of u with v plus w is inner product of u with v plus inner product of u with w, okay. So, again this is the axioms which I expect my inner product to satisfy, and a possible definition of this inner product is that is the same as what you do in your dot product, right. You take the adjacent coordinates, the same coordinates, and take the product, and then you find the dot product. If you have two vectors I, j, k, then you the corresponding i's you dot add it to the j's components, add it to the k components. So, that is basically what I have written here. So, this is the definition of the inner product, okay, and this is an extension of the dot product you are used to. Okay, where you take the corresponding elements and you take the dot product. First element with first element, second element with second, third with third. Now, again I want to, the one thing which I want to emphasize, that these axioms, and this is for alpha real, for real vectors, and when alpha belongs to real, okay. So, these axioms for the inner product are for a linear space where the field is real numbers and vectors have real elements as coordinates. Okay, I think this is something which you have to keep in mind, that these axioms are only for real. What do I mean by real? What is the opposite of real? Complex, okay, imaginary. And the question is, since we are solving chemical engineering problems, we will only have real variables, right? You can't have imaginary values for temperature, concentration. So, why are we even worried about it? The point is, when we are going to find solutions to problems later on, we will be using the concepts of eigenvalues and eigenvectors. And although your matrix can be real, your eigenvalues can be complex, your eigenvectors can be complex. So, you want to be able to incorporate that in your solution procedure, which means I need to generalize this for complex space. Okay. These axioms are valid as long as alpha belongs to R real and u and v have real elements. But I can have a situation where I may have complex elements, because when you do eigenvalues, eigenvectors, you can have eigenvalues are roots of a polynomial and they can be complex conjugate. Okay. So, therefore, you need to be able to generalize this to complex, which we will do now. But before that, I want to say that given an inner product, we can define a norm, and given a norm, you already saw we can define a metric. Okay. So, that was the hierarchy that I was talking about earlier. So, from an inner product, we can define a norm. Okay. So, inner product of u comma v is, we said sigma ui vi, okay, I equals 1 through n. And what is the norm of u? I can write the inner product of u with u to the power half, because this is sigma ui squared to the power half. So, inner product of u with u is nothing but sigma ui squared. That is what, when I spoke about length, I had this power half. So, the point I am making here is, given an inner product, I can define a norm, and given a norm, I can define a metric. Okay. So, that was the hierarchy that I was talking about. First, inner product, that is on top. If in a vector space inner product is defined, automatically concept of length is defined. If length is defined, distance is defined. Okay. That is the hierarchy. Yeah, from an inner product we can define. So, given this inner product, I can define the norm. So, I wanted to talk about the generalization to complex elements. Okay, your vector could possibly have complex elements, and what happens if I have complex elements? So, suppose U has complex elements. Yes, let's say U is, let us say 3i, 3i. Okay. Now, what is the inner product of U with U? Oh, maybe I should make this 4i, so less confusion. Everything becomes 3, then you don't know which 3 I am talking about. So, 3i and 4i. So, what do? What is inner product of U with U? By definition, sigma ui vi, sigma ui squared, right? So, 3i with 3i is minus 9, minus 16, minus 25. Is this clear? Because 3i multiplied by 3i gives me 9i squared, which is minus 1. So, minus 9. So, my point I am trying to make here is inner product of U with itself is now negative, okay, and that violates my axiom, first axiom, where I said inner product of U with U has to be positive. This violates is greater than 0. You have a vector, its projection on itself has to be positive. Okay. So, that is what we were trying to put there earlier. So, basically to emphasize, those axioms were only for real vectors, real scalars, but you could be dealing with complex scalars when it comes to eigenvalues and eigenvectors tomorrow. And so, we want to be able to generalize this definition. So, those axioms for complex spaces are useless. So, how do you generalize it? Okay. And so, the generalization to complex space, what is the of the inner product to complex space? That is the question. The complex vectors, complex scalars, okay, complex numbers. So, the field, remember vector space I said had two things, a field and a set of vectors. So, vectors will have complex elements, field will have complex numbers, okay, that is what I am talking about. So, this is now I am going to call this IC1 just to tell you inner product for complex. The first axiom is inner product of U with U must be greater than 0 and inner product of U with U equals 0. This is for U not equal to 0, for U equal to 0. That is the first axiom. And I want to have my second axiom as, so inner product of U with alpha V as alpha times inner product of U with V, okay, but inner product of alpha U with V I am going to write it as alpha bar inner product of U with V. I think I missed out one axiom earlier, we will see, okay. So, basically I have two vectors, if the scalar, the field variable is multiplying the second one, I take it out as it is, but if I am multiplying it by the, if the alpha multiplies the first vector, I take the conjugate, okay, and I see 3 inner product of U with V is equal to inner product of V with U complex conjugate. So, the bar represents the complex conjugate. So now what is this inner product of, okay, u with v plus w, that remains the same. Okay, that is, so I forgot to write this axiom in the real one. When I do the real, it will be inner product of u with v is the same as inner product of v with u. There won't be any complex conjugate, but this is fine. So I just want to explain to you how do you generalize this concept of inner product. So in complex space, inner product of u with v is defined as sigma ui bar vi through n. So if you have complex elements, okay, you will use this definition. This is a general definition. If it turns out to be real, then there is no question of complex conjugate. Okay. So, but if it is complex, you have to use this. So, this is a more general definition. So, inner product of u with v is sigma ui bar vi. If you use this, so now you understand, because this is sigma, what is inner product of u with v? Sorry, u with alpha v? It is sigma ui bar alpha vi. Okay, because I said scalar multiple means every coordinate gets multiplied by vi, by alpha. So this is the same as alpha times sigma ui bar vi, which is alpha times inner product of u with v. But if alpha multiplies by first vector, if I have alpha u with v, then I have sigma alpha bar ui bar vi, and this gives me alpha bar inner product of u with v. When I am defining my inner product by taking the complex conjugate of the elements of the first vector. So ui bar vi I am not conjugating. So for this definition, I am saying this will get complex conjugated. So when I pull it out, I get the complex conjugate. Okay, you can sit down and do this, but I want to make sure that the first axiom is satisfied, because that was where the problem was coming. So what is inner product of u with u? Let us go back to that other example. What was it? 3i and 4i. Okay. So now this is u. So now inner product of u with u is, take the complex conjugate of this minus 3i, multiply by 3i, I will get plus 9 plus 16, I get 25. Okay. I mean, just to tell you, because when you multiply something by the complex conjugate, you will always get a positive number, you get the magnitude of that. Okay. So basically, you need to use this definition of inner product, especially if you are dealing with vectors which have complex numbers as elements, and when you have complex numbers as elements, the field will be bunch of complex numbers. Okay. So that is something which you have to keep in mind. Okay. Thank you.